We'll start with a little introduction to the compilation, because it's an important part of what we will do during these 2 weeks. And the compiler do its best to do what you want, but sometimes it's not possible, and sometimes it's helpful, sometimes not. And we'll see that together right now. So basically, compilation means I want to translate text to binary. So I get in as an input, I have source files. Then I do some compilation, I get the object, so the .o, if you use make or cmake or stuff like this. And then we have linking, so we put all the object together and we will generate program on libraries. And they are supposed to run on certain hardware, so it could be CPU, GPU, we'll see that during this week. So during this process, we can do some optimization here in the level of the source. But of course, the problem of the compiler at this point is it does not know what you want to do with the others. So some optimization cannot be done because maybe you are reusing something in another file, so it's not possible. The only one we can do everything here is the optimization for the linker. You may have heard of LTO, for example, link time optimization. So it's a new feature for several years now. And if you have a big problem and you want to link that, normally you should have some improvement in terms of size of the binary. It's much more efficient to remove dead code, so something like this. So how does it work? So first, we start with your favorite language, of course. And then you have, we want to get binaries. What's the point to be in there? So first, we want to translate the language with a front end. So the front end to check the grammar of the language, all the syntax of the language. And then we jump to the middle end, so the intermediate representation, if you want. So we have lots of intermediate representation, but let's presume there is one for this slide. And with this middle end, the point is to have an abstraction of your language at the beginning and do some optimization on it, or some passes in a generic way. So the first one might be to remove some comments, because you don't want comments in your binary. And then you can maybe resolve macros. But then you resolve macros, and maybe macros will create some comments, so you can remove comments again. And maybe, yeah, we can remove dead code because we have macros, maybe they resolve something, and we can remove dead code. Then you can increase the compilation flags, and you can do some constant forwarding. So instead of having a value a fixed value inside a variable, you copy directly the variable where you want to use it. So you don't have to do that, the compiler does it for you. And maybe you can remove useless code with that, because you can, so with the dead code, maybe you have a part that you don't use and you don't have to call this function, so you remove the function. And maybe you can also remove dead code with that. And sometimes maybe you want to see what's going on in the loop themselves. And you will figure out that in fact the loop is not necessary. So you can remove the loop, for example, or you can simplify it. And you see it's a kind of a recipe. And then you can also remove useless code, stuff like this. So there is a lot of passes in a compiler. Every compiler has this kind of ordering for the different passes. And the point is, a pass is quite costly, in fact, and it's better to call the pass, even if the pass does nothing, rather than to check if the pass should help at some point. So that's why they have this kind of way of doing it. In a classic compiler, we have between 150 and 300 steps, 100 passes inside the compiler. That's why it can take something like 1 second to compile one file of 20 lines. It's possible if you enable everything. And once it's done, you have something which is normally quite common, and then you use the backend and you produce a binary for the hardware you want. And the backend will read the the technical part of the hardware to say, okay, for example, when I do a add, I want to have this binary. When I do a sub move, this binary, etc. So the core of the compiler is the intermediate representation. So first, if we take a really simple program, the program will be a graph. And what's interesting in this graph is we can update it if we need it. So for example, we can add probes. That's the case when you are using, we want to check some instabilities for the numeric purposes, or you can use maybe gprof for profiling, and it will have some probes into your intermediate representation. Or you can do gcov for the coverage, so we'll have basically counters for the line and branches, so to count how many times you reach this line of code or this branch. Then we can do a lot of optimization, so constant forwarding, inlining, auto-vectorization, auto-parallelization. We'll see that, of course, in the school. And one rule is results have to remain identical to what was in the input for the compiler. The compiler is not allowed to change what you are supposed to do in your code. And the graph needs to be similar, the output graph needs to be similar as in the input graph. And the point is, sometimes the graph theory forbids some optimization. The compiler is dumb, it just cannot do it because the graph is not the same. You can, as a developer, say, okay, I want to do this optimization, but the compiler cannot help you because of the graph theory. So, in terms of options, so I give you the documentation of GCC, but you have the similar documentation for your favorite compiler if you want. So basically, for O0, there is no optimization at all. It is the default compilation flag. So if you have no flags, you can have a speed up of 15 just by changing a flag. So do it. Normally, it should be nice. Then O1, we do some constant forwarding, remove some dead code. Not too much, but just a few. Then partial inlining for the function, and we assume also strict aliasing. And then O3, more inlining, we start to unroll loops depending of the flag with a partial vectorization, sometimes not in all versions of GCC, as we will see. And for OFAS, you try to do some magic with fast math, with rounding, with stuff like this to have a speed up. As Vincent said, you have to do that, but carefully, because if you want to have nice results, you have to be sure that you do that on purpose and can do that without problem. So let's start with an example. Let's start with this square program. So we have a program to compute the square of a value. So first thing I can do is to do some constant forwarding. So instead of having the y variable here, I put directly the value of this variable where I call it. So I don't have to get the variable on my registry, stuff like this. I get directly the value. It's nice. Then I can say, okay, I can inline the function because the function is really simple. So I can directly copy-paste what's in the function instead of calling it. And then the compiler will say, okay, but now I can do some math with it. So you can you can solve your expression with as a constant. So compute the 42 times 42, you have 1764, and that's it. And by doing that, you have no more function call, no more multiplication, and no more variable declaration. That's why sometimes you want to profile a code and you say, oh, my function is not, because you have an inline. So let's try also to do some unrolling. So as I said to you, you can have some trouble also with the pipeline. Let's have this basic example. Of course, it's an AdBar product because it's one of my presentations, you know. And then we can unroll twice. So the idea is to take the body of the loop and to do a copy-paste of the body and increase inside it the iterator of 1. So we have a bigger body of the loop. And So it increases the computing of an iteration, and the compiler can do some optimization. Maybe you can have some part in common between two iterations of your compilation, so the compiler can say, okay, I can factorize this compilation, and this when I do the computation, and everything will be more efficient in terms of registry, register, something like that. And you can also 4 times more, in fact, if you ask the compiler gently, and you increase the body of the loop, and more important of that, you diminish the number of time you check if the loop ends. So without unrolling, you check if you are in the end of the loop, and then you do an iteration, and you check again if you are in the end of the loop, and you check again, etc. Sometimes it's not really great because your loop is really small, and your iteration is really small, and you have a lot of iterations, so you don't want to check every time. So you unroll, and you diminish the number of time you check. You diminish also the number of time the branching predicator could go wrong. So it's better, and normally, if you don't ask a branching predicator to do a prediction, normally it cannot go wrong. So it's a good point. Another point which we will use a lot on this school is for load and computing optimization. So first, if we get a 3x3 kernel load without unrolling, you get your computation and you compute one result, and then we have 9 loads per store, which is quite a lot. A CPU is designed to be efficient with 2 loads per store, or triadic, basically. So it's quite a lot. Let's diminish that. So we can try with unrolling 2 times. So we have the first kernel with 9 loads, and then we have the computation, and we do the next one. And here we have to load only 3 values. Better. So we get 12 loads, but 2 stores. So 6 loads per store is better. And then we can unroll 4 times. At the same time, we have the first one, we compute the first one, we have 3 for the second, 3 for the third, and 3 for the fourth. And here we get 18 loads and 4 stores. It's way better because here it's 4.5 loads per store. Of course, it's a stencil in 2 dimensions, so it's quite difficult to do much better than this. And at some point, the compiler might be a little annoying with you because you don't have enough registers. And the compiler knows it. And maybe you forgot. And you want to enroll, and the compiler will say no. And yeah, maybe if you force it, you will see that, okay, the compiler was right. I didn't have enough registers. So you have also to take that account. It's nice to diminish the number of check and to unroll loops, but sometimes you will have some problem with registers. You can also suppress some sub-expression if it's possible. So if we have this kind of expression, a plus b plus c times b plus c, we get a graph. So 2 loads and add, 2 loads and add, and we do the multiplication and we get the store. Nice. So in terms of computing, we get load b, load c, then we do the add, and then we do load b, load c, add, the multiplication, and the store. That's a bit bad because we have too many nodes, of course. So what the compiler will do is to say, okay, we use duplicate result of add. So we do the first add, we duplicate the result, and then we call the multiplication. It's way better for the memory. You do only one load, as Adrien said. Also, regarding the pipeline, once you do a load, but it's not the right load or a store without the, here you have a better. Yeah.
And the duplicate, where it is in the what takes what place it takes in the memory? Because if we load twice B and C, we have 4 address in the memory, but the duplicate, what's going on?
The point, yes, you have to think with the stack with this kind of approach. The point is you load B in a register, you load C in the next register, you do a add of the two to have one result with the one register, you duplicate this result, so you have one result. So to do an operation of this, you have to have two values. So the point is you get the first one, duplicate it instead of loading the other one, and then you perform your multiplication of these two values. It's a stack problem. The compiler does a lot of optimization based on the stack, in fact. So you don't have much memory. Yeah. That's a trick. Yeah, we did not have time to talk about the stack much, but yeah, that's a trick of about the stack. And then we store the value of A, and the good point is, of course, we have one, we suppress a lot of load. So let's try to do some performance test, as we will do a lot during this course. So let's take an Adama product, of course. So this kind of function, no problem. So we have well-defined variables, and let's implement the function to do the performance check. So we allocate some values. They are not aligned for now, but it's not a problem. Then we do some initialization. We start the chrono, and then we do some performance evaluation. So notice you have a number of repetition because maybe calling one time is not enough. We want to have a bunch of values here. So we'll have time to play with that during the school. Then we stop the chronometer. We compute some time, and we do some plots. We print the result, and we don't forget to deallocate everything. And everything is nice. And if I ask on several values, hard-coded values, not really elegant, but that's an example. I ask G++11, I will get this kind of result. So here it's expected performances, nothing to say, it's nice, quite okay. So you have on the left the total amount of time of the computing, and on the right you have the total amount of time per element. So it's nice also, you see the nice plateau when you change cache, something like this is quite nice to have in mind. But there is a problem. What is it? 1/1000th of a nanosecond to compute 1000 floats on a single course? It's a bit too much, maybe? So this is equivalent to 1 petaflop per core. So my laptop is good, but not that good, let's be honest. There is a problem. Okay, let's change compiler. I use Clang. Okay, I get the same. There is a problem. Okay, let's switch to ICPX. Still the same problem. At some point, once you go in this kind of trouble, you have to think like the compiler and say what's going on. So let's take this implementation. The compiler will check the result first and say, okay, the result is here, no problem, except that we don't use the result. There is no print, there is no return. What's the point to compute the result? So let's remove it. So then this for loop is useless because it's empty. So let's remove it. But then these variables, they are set, but they are not used because the loop disappeared. So let's remove them. And finally, we get this useless loop and remove it. And we get the stop and the start of the chronometer next to each other. So we have an elapsed time of almost 0 each time. And we print that, and it's strange. And this is the case because the kernel is in the same file than the function we have here to check the performances. And the compiler can prove the function is pure, as Vincent said before, so no tricks, no ugly global variable somewhere hidden that you can do crazy stuff with it. So it's nice, we can optimize, no problem. But the problem is you don't want that. So to avoid the problem, you can split the file. You can say, okay, I put my kernel in one file and I put my check of the performance in another file. The compiler will not see the two files at the same time, so will not be able to optimize this. Or you print the result. That's what we do mostly in all the courses. And if you use a std vector, the compiler will say, okay, it's a big class, I don't understand really what's going on, so I do nothing. Because you can hide some other stuff in this kind of class, so there is no problem with that. So if you fix this problem, you get this kind of performances. So if we compare G++11 and Clang 14, we have the same performances for 0, normal, we don't do any optimization. O1 it's quite the same, but O2, O3 and OFast, Clang++ seems to be quite better. Here, they are here, and here they struggle here. And at this point, I'm not saying that Clang is better than G++. The point is, they disagree of what is O2, O3, and OFast. Once G++ will say, okay, I'm in O2, I do nothing, Clang will start to vectorize a bit without really knowing what is the architectures, but let's try in SSE4 here. O3, OFast, Clang cannot do much because it's just an Adama product, but G++ will try also with OFast here to do a pseudo vectorization, partial vectorization here, but only in OFast, not on the other. But on the contrary, if I ask them both to do vectorization, they're perfectly equal. It's normal. Once you get the performance, the max performance you want, you get them. And here, I have the same performances here than here. But they disagree on what is what should be the optimization on O3 here, for example, compared to this one. Here you get the half vectorization. Here you get the full vectorization. So this is AVX and this is SSE4. So let's talk about a nice mistake that Adrien already presented, but I love this one, so I'm obliged to present it to you. So you have a nice function. The function is well defined, everything is nice, the data are allocated, they are aligned, you have all the optimization options which are okay, no problem, everything is nice. What is the problem? I know we are late, so there is no problem. The problem is the for loop has an unsigned int, and I pass a long unsigned int. And this is quite common if you are using vectors. For example, if you do a dot size, you get a long unsigned int as an answer. And the point is, the compiler will say, okay, but the condition here could be always true. The maximum value you can put in an unsigned int is 2 power 32, so 4 billion something. If I put 5 billion elements, I'm stuck. I have an infinite loop. This is quite annoying. And the point here is, we'll talk a lot, I think, on Thursday about undefined behavior. This is a defined behavior. Once you have an overflow and an unsigned, you know what to get every time. So the compiler knows for sure you cannot reach, in some cases, the boundary in your loop. So you have an infinite number of iterations, and the compiler asks itself this superb question: does infinity a multiple of 8 if you want to vectorize, for example, on AVX, or 16 on AVX 512? And of course, the answer is no. So there is no vectorization at the end, just because of that. Just because the compiler cannot prove that your number of iteration is not finite. So It's important to have that in mind. So let's talk briefly about reduction now. So reduction, as Adrien said, we want to sum values. What can we do with that? So in C++, we can do that. A little for loop with a long unsigning to be sure that we are not stuck with the number of elements. Every time you do a reduction, you have to think about Vincent on your shoulder telling you that remember the number of value you want to sum. At some point, if it's 1,000, it's nice. If it's 1 million, maybe you will have a problem. So here it's 1,000, so it's okay, even if it's not written in the slide, but always ask you this question. We can also, we have a definite order, it's not necessary here, and we can rephrase that with std reduce if you want to have more, to be more gentle with the compiler. So if we do that with G++11 and Clang 14, we say that they agree globally on what's in O3 here, and O2 and O1 and O0 also. But for OFAS, they Clang tries some stuff that G++ does not try. But it's not vectorized, so what's the point? Okay, let's vectorize. And here, the funny stuff is they are stuck. They are perfectly equal. And I can say, yeah, but if I do the same with intrinsics, so the idea is to force the compiler to do what you want to do. So you call the intrinsic function by hand. It's not portable, not well portable. You can use SCMDE if you want to have more portable stuff. But to try to check if the compiler can do better or not is nice. On a really small test case, it's nice. So what's going on? Here I compare the loop implementation. And the problem with the loop implementation is the compiler is forced for each iteration to return a scalar. So you can do, you load a vector register, you load another vector register, you do the sum, but then you have to return a scalar. So you want to reduce the vector and to go out with a scalar. And then you do the next iteration. And that's a bit bad. Because here, I do what you all want to do. You start with a vector register of accumulator. You use that during all your for loop, and then you reduce, but just at the end, not inside the loop. But the compiler cannot do it because of the graph theory. So what we can do is, and here we have a 10x, by the way, what we can do is to use the std reduce, which allows the compiler to do this kind of stuff. That's why we want to use std reduce. And then it's much better. And here we have a reduction here, so it's way better than before because we let the compiler do the work nicely and we do not force it to have a scalar as a result because we don't care because we are in an iteration. But we can do better. Of course, we can do better. We can do that. Reduction with interleaving. So how does it work? So how to optimize a reduction? Basically, once you do a reduction, you do some computation and you have an elapsed time inside the processor, and you have to wait until the result can be used again. That's a latency, if you want, by the hardware. So you can vectorize, no problem, but you still have to wait until the result is reachable. And of course, if you want to reduce with one accumulator, mainly you wait for the next result to come. If the computation is really small, it's quite problematic. If you have a lot of much more computation, so by center with a lot of dimension, normally there's no problem. But for really small computation, it's problematic. So to optimize that, we can use two accumulators. And I cannot compute in the two accumulators at the same time, but since the first one is waiting, I can compute the second one. So then I do a bit of interleaving. I can have a speed up, not always, but in this case, with a really simple example, it's working. And in this schema, I can do with 4 accumulators, and here I can have a computation each time for each accumulator. I have a computation. I have a good speed up here. That's why we can have the this kind of performances. So I have the nice reduction vector at the first one with the for loop. Then we can use the intrinsic. Then we can interleave twice. Then we can interleave fourth, and then we can interleave 8 times. And you can see also that E++ is smarter here because he knows that he can unroll your interleaving, so it's quite the same as Clang. So some reminder, I'm pretty sure that Adrien will tell that to you tomorrow, but once you do performance tests, you have to ask yourself, are we measuring what we think we are measuring? Because there is much thing to come, a lot of factor in it. So once you do a performance test, you evaluate with a given method. So with a more or less precise chronometer, maybe it's not the good one. The one implementation, so with more or less quality, of an algorithm, but more or less relevant for your problem. With compile, but with more or less useful flags also. Sometimes it's not necessary, sometimes there is one missing. On a computer, more or less efficient, with more or less caches, with more or less shared resources. Maybe other jobs are doing some crazy stuff with the I/O next to you and you don't have bandwidth. With a dataset, more or less representative of the problem. So maybe you will have none on the normals and stuff like this. Vincent will present them also in this week. During an elapsed time, but maybe it's not that pertinent, not that relevant. Maybe it's too short, maybe it's too long for the problem you want to treat. And on a certain operating system, which is more or less terrible to use, depending on what you want to use. And once you get a result, you have to think about all these points because they influence the results you get. So that's why once you change machine, you change OS, you do some upgrade, you can have different version. I speak about the OS, but of course there is a kernel under it also. So you have to be careful about that. So I will start, yeah, we have a bit of time. So I will finish with a little funny thing about compilers coming from our colleague of INRIA. It's about certification and compiler testing, because a compiler cannot fail, a compiler cannot have a segmentation fault, a compiler is always right, and a compiler cannot produce wrong code. But it was not always the case. So a compiler, it's really, really hard to develop a compiler. I assume you have a brief view of what is the difficulty behind it now. And sometimes you need a certification. For example, if you want to do some control for a plane, because of course the programs are certified, but the compiler to compile the program have also to be certified. So otherwise you can have a problem, especially with a plane. And one team of the INRIA developed Dismiss. So it was a project. It's a bit old now, but the idea is really brilliant. The idea is to say, okay, let's create a C generator of code. So perfectly well code. So it's part of the grammar of the C, but the point is to test all the edge cases that compiler people cannot think about, because you cannot think about everything, of course. And they run that on all the compilers they had at the time. So it was about 14 years ago, something like that. Yeah, 14, 15 years ago. And they discovered more than 100 bugs in G++4, Clang at this point, all the compiler of this time. It was really, really a catastrophe at this point. So if you are still stuck with G++4, I'm sorry for you. because you will have some trouble. So the good point is now all the bugs are normally more or less fixed. And when I talk about bugs, it's not you have an internal error in the compiler. Normally, it should not happen, but if it happened, okay, that's a bit annoying, but it's not problematic. It's not, okay, the compiler crashes. It's a bit problematic also, but it's not what we call a bug here. What we call a bug here, it's you compile, the compiler is happy, and the binary is wrong. That's a bug in that case. And once you want to fly a plane, would be quite problematic. So that's the first part of the story. The second part of the story is the same team said, okay, it's nice to break a compiler, but let's build one. And they built Concert, which is a certified compiler. And when I said certified compiler, it's based on a mathematical theorem. So it's really elegant math behind it. And the point is to have, you can do everything you want in terms of entry. If it's compiled, the code will be nice and will be relevant. So it's possible. We will not talk about that during this call, but it's possible if you want to have certification. It's possible. It's really hard to do, really hard, but you can have a look if you are interested. So it's a mathematically proved C compiler. If you want to have a look, it's always nice. So in conclusion, do not choose a compiler, use them all. And check every time with Macao, with Valgrind, with all the tools that we will present to you in the school, if the compiler does its job well, if the binary is correct, if the vectorization is enabled, if it's not, you have to understand why. And don't forget to do some micro benchmarking to be sure that your kernel, you understand what it does. And if it's not the same behavior with in another project, maybe we have a problem of data or something like that. And thanks for your attention. So in the satellite site, maybe you have question, or maybe here you have question. Or no, not yet. So we're on time now, so we have time for question.
These loop unrolling techniques are done by the compiler or by the programmer?
The unrolling, the simple unrolling is done by the compiler. So you can ask Clang or G++ to unroll. You can use some pragmas if you want to unroll a certain amount of loop. And sometimes G++ will complain and say to you, no, I don't want to unroll 8 times because I think 6 is better. and that's it. And you can force Clang to do 8 and you will realize that G++ was right, and that's it. But yeah, you can control that with pragma, with option also. You can do that in NVC++ also if you want, or in DPC++, or ICPX. You can force to check, you can force, and then you get the best one.
Thanks.
But interleaving, the compiler cannot do it. Because it breaks the graph. So you have to do that by hand. In fact, we do not use this kind of stuff in production, but just for a simple test, you say, okay, I can have this speed up in case of emergency that we have too short for something. But just in case of emergency, of course. You have a little room for improvement. It's always nice to have in mind. What are the nodes and edges in the graph representation of the compiler? Basically, you have in the internal representation, they call that independent of the compiler, but it could be statement for G++, for example. Basically, you have one statement be one operation, one variable, one call, one condition, one loop. And the point with the loop is tricky, is in the internal representation that we have, for example, in G++, there is no loop, in fact. You have a graph, and at some point, you have a node, and you loop. And you have to walk on your graph and say, okay, did I pass already in this node? And you say, oh, this is a loop. This is quite annoying once you want to create a plugin inside G++ to do this kind of stuff, because it's graph theory, but in C. It's a bit better, but at the time we did that, it was in C. And what a nightmare. Of course, it's better to have something high level. So you have a for loop, you have a body, and you do some stuff. But if you do that in terms of graph, you have a bunch of graph, and you have to iterate and say, okay, that's what's a loop, in fact. So yeah, basically, edges is just to have the ordering of the nodes, and a node could be yeah, variable, condition, definition of a variable, operators, stuff like this. But yeah, once you your first plugin in G++ and you know how to export your graph in dot to have a nice graph, we are really proud of you, because it's really difficult to do.
Okay. How often do you try to do optimizations on the intermediate representation instead of like at the compiler layer? And how do you do that? Like, let's say you're targeting the like the LLVM. What are ways that you can instruct it or pass more details to it so that it can try to do more optimizations at the next layer?
It's by mainly the flag. So you pass O3 or fast or 2 or something like that. You can enable also. The point is, once you use OFast, for example, it's enabled fastmat, but you can enable fastmat even in O2 if you prefer, because you just want this one, not all the stuff that comes with OFast, for example. So you can have, so it's you have a lot of detail in the documentation of G++, for example. But the point is you can check. It's really well documented. In fact, you have really the passes and what is done by the pass. So you can really check really in fine grain what you want to optimize. But at the end, you get 5 kilometers command line to compile your stuff.
Getting too detailed, you're basically writing like code into the compiler itself that talks to LLVM if you wanted to get even more detailed.
You can with pragmas.
Okay.
If you want, you have a pragma unroll something. I don't remember the something, but it's pragma unroll something. In the documentation of LLVM, you have that. In G++, you have that also. In ICPX, you have that, but it's not the same one, because why not? So yeah, again, once you start to use pragmas, you have to jungle with a lot of compiler. Quite annoying, but you can do it. And sometimes you also have to, don't forget that you put this pragma on your code and you change the scale, and the pragma says with a number of unrolling fixed or a number of thread fixed, and you scale and you forget this one. And you, why I lost my performances? Yeah, it's because of, yeah. So you have to be careful about that. Yeah, but, yeah, you can. If there is no more question,
are there some optimization that can be applied at the linking part? Because all the optimization are during the first part, the compilation. Is it right? Yeah.
Yeah, you have optimization that can appear in the linking part, because the linker is the only one who can see the whole program. So once you are linking, you know for sure what you will create. It's the final product. So you can have a look and you can say, okay, this function is never called, even if it was compiled in separate files. So you can drop it for sure. Intel tried that at some point, and they renounced it because it was too complex to do it. Now NVIDIA does the same, and it's coming also in the LLVM, and now it's working because it's quite problematic. In fact, you have to work on your graph of the call and to say, okay, everything which is out of this graph, I remove. If you do the opposite, you have a complexity problem. You don't want to do the opposite. But yeah, mainly it's for dead code removal. Pretty sure there is another one, but I forget it. So, but mainly it's for dead code removal. But you can also do maybe some constant forwarding or something like that at larger scale. To say, okay, I define it here, but I use it there, and it's constant, so no problem. You can do this kind of stuff.
Okay, thank you.
But yeah, really simple stuff. In fact, not unrolling, not stuff like this, but little stuff, but makes your binary smaller, so you have less jump or smaller jump. It's more efficient to reach your function once you call it. You have a nice binary at the end.